This video is about chemical equilibrium, specifically focusing on the first section about the state of chemical equilibrium. We will explore the state of chemical equilibrium in this section. The performance indicators for this lesson include recognizing the concepts of equilibrium, complete, and reversible reactions. We will differentiate between homogeneous and heterogeneous equilibrium and apply the mathematical relationship for the equilibrium constant to solve problems. Finally, we will illustrate the importance of equilibrium in our lives with examples. What is the state of chemical equilibrium? Chemical equilibrium is a state where the forward and reverse reactions balance each other because they occur at the same rate. In life, similar to a tug-of-war game, even if the rope appears still, both teams are pulling. The forces exerted are equal and opposite, resulting in a state of complete equilibrium. Chemical reactions reach an equilibrium point when they occur at the same rate in opposite directions. The preparation of ammonia occurs spontaneously under standard conditions, which are 298 K and 1 atmosphere. However, spontaneous reactions are not always fast. To produce ammonia quickly on a practical scale, the reaction must be carried out at a higher temperature and greater pressure. What happens when 1 mole of nitrogen and 3 moles of hydrogen are placed in a closed vessel at 723 K? Since the reaction is spontaneous, nitrogen and hydrogen will react. The graph shows a decrease in the concentration of reactants, N2 and H2, initially, while the concentration of the product, NH3, increases. Before the reactants are completely consumed, all concentrations become constant, which indicates the system has reached a state of dynamic equilibrium. The forward and reverse reaction rates become equal. In the graph, the concentration of ammonia, NH3, starts at 0 and gradually increases over time. The reactants, N2 and H2, are consumed, so their concentrations decrease but do not reach 0. After some time, the concentrations of N2, H2, and NH3 stop changing. The dashed vertical line indicates the point of equilibrium. To understand the shapes in graphs, describe the slope values of the curves for the reactants and products on the left and right sides of the dashed vertical line. The slope of the reactant curve is negative on the left as it decreases. The slope of the product curve is positive as it increases. On the right, the slopes of all curves are 0, meaning no increase or decrease, as the concentrations stabilize. A complete reaction is one where reactants are almost entirely converted to products. Most reactions do not go to completion and seem to stop because they are reversible. A reversible reaction is a chemical reaction that can proceed in both forward and reverse directions, such as the example shown here. In Figure A, we know the reaction has not started because only the reactants are present. In Figure B, the presence of more than 2 ammonia molecules indicates that the reverse reaction has begun. Compare Figures C and D. How can you tell that the system has reached equilibrium? The number of reactant and product molecules is the same in both C and D, and the concentrations of reactants and products are restable. When the system reaches equilibrium, concentrations remain constant. This doesn't mean reactions stop, but rather that the forward reaction rate equals the reverse reaction rate. Chemical equilibrium is a state where the forward and reverse reaction rates are equal, and the reactant and product concentrations are constant. The double arrow in chemical equations indicates that the reaction is at equilibrium, and that the forward and reverse reactions are occurring at equal rates, which is a state of dynamic equilibrium. This relates to physics, where forces in opposite directions are balanced. Consider the example of a glass walkway connecting 2 buildings. If all entrances except the walkway are closed, and the same number of people cross the walkway in both directions every hour, the number of people in the buildings remains constant, even if the numbers in each building are not equal. Equilibrium only requires that the number of people crossing the walkway in one direction is equal to the number crossing in the opposite direction. We can illustrate the dynamic nature of equilibrium with the following example. 2 flasks, connected by a valve, contain equal masses of solid iodine crystals. One flask contains non-radioactive iodine 127, and the other contains completely radioactive iodine 131. The right flask indicates radioactive iodine 131, while the left flask contains non-radioactive iodine 127. When the valve is opened between the 2 flasks for a period of time, the radiation detection device indicates that the radiation levels become constant. This is because radioactive particles are moving back and forth between the flasks and between the solid and gaseous states, establishing equilibrium in the total volume of the flasks. The system is closed, as matter cannot enter or leave either flask. The physical change shown is sublimation, occurring at 298 K and 1 atmosphere. Some chemical systems do not proceed far in the reaction, while others continue until completion. Most reactions reach equilibrium without consuming all reactants, resulting in a product quantity less than the theoretical yield. For example, in the ammonia reaction, 1 mole of nitrogen and 3 moles of hydrogen are expected to produce 2 moles of ammonia. However, less than 2 moles are obtained because the reaction reaches equilibrium. The equilibrium constant, Keq, is the numerical value of the ratio of the product of the concentrations of the products to the product of the concentrations of the reactants. Each concentration is raised to a power equal to its coefficient in the balanced chemical equation. The value of Keq remains constant at a specific temperature. If Keq is greater than 1, the product concentration is higher than the reactant concentration at equilibrium. If Keq is less than 1, the product concentration is lower. Homogeneous equilibrium involves reactants and products in the same physical state, such as gases, as in the formation of hydrogen iodide. First, write the product concentration in the numerator and the reactant concentrations in the denominator. Then, raise the concentrations to the power of their coefficients in the balanced equation to obtain the Keq expression. Keq has a value of 49.7 at 731 K and is unitless. Here are 2 more examples of how to write the equilibrium constant expressions for homogeneous reactions. Homogeneous equilibrium refers to reactions where all reactants and products are in the same physical state. This scene shows examples of writing the equilibrium constant expression, Keq, for several homogeneous reactions. The expression places the product concentrations in the numerator and the reactant concentrations in the denominator, each raised to the power of its coefficient. It is not necessary for the concentrations of the substances in the previous reaction to be the same at equilibrium. The concentrations are not equal, but when the equilibrium concentrations are substituted into the equilibrium constant expression, the same Keq value of 49.70 is obtained in all 3 cases. Since Keq is greater than 1, the concentration of the products is higher than that of the reactants at equilibrium. If Keq were less than 1, the opposite would be true. Heterogeneous equilibrium occurs when reactants and products are in more than one physical state. Pure liquids and pure solids are not included in the equilibrium constant expression because their concentrations remain constant and do not change. We must write the Keq expression for these reactions, omitting any pure solids or liquids. Here is a table showing examples of heterogeneous reactions and their corresponding equilibrium constant expressions. Notice how pure solids and liquids are excluded from the Keq expression. Here are additional examples of how to write the equilibrium constant expressions for heterogeneous reactions, including the dissociation of a pure solid. Here are more examples of writing the equilibrium constant expression for various heterogeneous reactions, including those involving aqueous solutions, gases, solids, and liquids. Experiments show that the Keq value for a specific reaction remains constant under the same conditions, regardless of the initial concentrations of reactants and products, provided the temperature and pressure are unchanged. The table illustrates 3 experiments for the hydrogen and iodine reaction. Although the equilibrium concentrations differ, the calculated Keq value is the same in all 3 trials, confirming the stability of the equilibrium constant. The characteristics of chemical reactions that reach equilibrium are: the reaction must occur in a closed container, the temperature must remain constant, and both products and reactants must be present in a dynamic state. Dynamic equilibrium means that the forward and reverse reactions are continuously occurring at equal rates. The 3 graphs here illustrate the changes in concentration for the same reaction under different initial conditions. In all cases, the reaction reaches dynamic equilibrium, where the concentrations of reactants and products become constant over time.